Yeah. Okay, thank you. So this is joint work with Monique Laurent, and what I will talk about is a conic approach to entangled-assisted graph parameters. So hopefully I will explain to you what's entangled-assisted graph parameters. But for the purpose of this talk, we will focus on the chromatic number. So let's start with the classical definition. For the chromatic number, we have a graph. What we want to do is we want to assign to each vertex a color, such that adjacent vertices receive different colors. And the chromatic number is the minimum number, such that minimum number of colors, such that such a color exists. So Shabata had a nice observation on what's the chromatic number of a graph. He defined it as in terms of the stability number of a product of graphs. So G Cartesian product, a complete graph, is the following graph. We take our graph G and a complete graph in this side. The vertices is the Cartesian product, so we make a grid. And for the edges, we do the following thing. We add horizontal edges if there was an edge in the original graph G, and we add a vertical edges if there was an edge in the complete graph. So we add all the possible vertical edges. And what Shabata observation is telling us is the chromatic number is the minimum integer, such that the stability number of the Cartesian product graph between G and the complete graph on T nodes is equal to the number of vertices of the graph. So let's see why this intuition works. So this graph G is not bipartite, and with 3 colors we actually can color it. So the chromatic number is equal to 3. So here I put the complete graph on 3 nodes. So we have 3 nodes. We can label the nodes of the complete graph by colors. So let's do that. And now we do the following coloring procedure in the Cartesian product graph. So let's take a vertex, U. What we're going to select? We're going to select the corresponding vertex in the Cartesian product, which is labeled by the color. So U is red, so we're going to select U red in the Cartesian product graph. This one is blue, so we're going to select this vertex. And we go so on so forward. So how many vertices are we going to select in the Cartesian product graph? Exactly the number of vertices of the graph G. Just because for every vertex we pick exactly one vertex in the Cartesian product. And now it's not even hard to see that the vertices that we pick is indeed a stable set. So every pair of vertices, they are non-adjacent. And the reason why this is just because of the orthogonality, the edge condition in the Cartesian product. So what's this Shabata observation is that the minimum T is such that you can build such a construction. Oh, okay, sorry. So this is a stable set, this set I color, but it also is a maximum cardinality stable set. Why? Is because if let's say I want to color another vertex, you must color 2 vertices on a vertical line, and these are going to be adjacent because I have all the vertical edges. So this is also a maximum cardinality stable set. And Shabata observation says that the minimum T, such that you can make such a construction, is actually the chromatic number of a graph. Indeed, you can also start from such a construction, and such a construction give a coloring of a graph. So that's the intuition. Why do we want to go in such a kind of complicated way to describe the chromatic number? Is that we can think about the vertices of the Cartesian product graph as variable, x, u, I, where u is the number of vertices of G, and I is the number of colors. These are going to be 0, 1 values. And in this way, we can write a 0, 1 linear program, which describes the chromatic number. So this linear program is exactly this observation up here. What we want, we have a variable x, u, I, and we're going to, the values, the variables that are going to be assigned with a 1 is going to be corresponding to a stable set. So what are my constraints? Is that if we fix a vertex and we run over all the possible coloring, exactly 1 variable is going to be assigned with 1. So so the number of variables that are going to be assigned by 1 is going to be the number of vertices of the graph. Moreover, we add all the edge constraints to ensure that the variables are going to be in a stable set. And the chromatic number is the minimum T such that such a variables exist. Now, we want to have such a program because we will see that the quantum version of the chromatic number, it has a really similar formulation. So what's the quantum version of chromatic number and how it does it come into place is because of non-local games, which are a theoretical physical framework to study quantum physics versus classical physics. So it's a really easy framework to study the property of entanglement. So this is, in some part, is a talk about quantum information, and in quantum information we always have Alice and Bob, so here they are. We have Alice, we have Bob, and we have a referee, which is, in this case, is their grandfather, and they're gonna play the following game, which is called a coloring game, and it's a non-local game. So the game is as follows. So Alice and Bob and their grandfather, they're gonna decide upon a graph they're gonna play on. So once they decide the graph, they can decide strategy, they can talk, they can do whatever they want, but once the game starts, Alice and Bob go in separate room and they won't be able to communicate. So what's the game is each of the two kids are gonna receive a vertex. So let's say Alice receive a U and Bob receive a V. And what they have to output, they have to output colors. So they have to tell them individually without communicating a color. Let's say Alice replies I, Bob's reply J. And what's the condition we want is that for a given pair, if the two vertices were equal, they must output the same color. If the two vertices are adjacent, they must output different color. So somehow they're gonna convince their grandfather that they can color the graph, but on a pair of vertices. So we don't require them to be consistent, in the sense that if in one instant we ask them, we send them UV, and in another instant we send the same vertex, we don't require them to output the same type of colors. We just want this condition to be respected. Okay, so it's not a proper coloring, it's a coloring on two vertices. So what's the idea? Okay, so we want them to play this game, but what's a kind of a stupid strategy they can have is what they can do is that they can color the graph with n number of colors with n number of vertices. So what happens if they do that? They're always going to win the game, because so they just decide upon just coloring each vertex differently. Then if they see the same vertex, they reply the same color, and any different pair of vertices are going to have different colors. But that's not interesting, so that's not going to tell anything more. So what we want the value of the game, and the value of the game is the minimum number of colors such that they always win this game. Okay? So what's the optimal classical value? It's actually the chromatic number of the graph. Okay, so let's see one implication. So think about the following strategy. So they know the graph beforehand, and they can decide a strategy they can play on. So what they can do is that once they receive the graph, they color the graph, assuming that they are able indeed to color it. And each of them are going to have two pair of, are going to have like a copy of the graph with the same coloring. They go into separate rooms, and now the only thing that they have to do when they receive the vertex is just to look which color they have and reply that. And indeed, because it's a coloring, we have both of these conditions satisfied. And it's not hard to see that also this is the optimal classical strategy they can have. They cannot do any better than the chromatic number. So where does the quantum comes into place? Now we assume that the two players share an entangled state. So they have more resources than in the classical world, and they can use this entangled state to do local operation or measurement. And the question is, does this having an entangled state help? Can they do better if they still won't be able to communicate, but they can do operational entangled state? So this game was formalized by Cameron and co-authors in 2007, and the optimal entangled system value of this game is called by chi-q, which is the quantum chromatic number. So the reason why I'm talking to you about this is because such a separation exists. So having entanglement between two players does help them in some special cases. So what is happening is somehow the player seems to be able to color a graph with less number than the chromatic number of colors. So something quite counterintuitive is going on. But indeed, quantum theorem allows us to be. Because we want the color appearing only on 2 pairs, so it's not a real color, it's that it's on every instance they're able to color only a pair of vertices. So let's see a couple of properties of this parameter. So this is the parameter we're interested in studying. So for bipartite graph or MP graph, nothing interesting happened. So quantum chromatic number is equal to 2 if and only if the chromatic number is equal to 2. There exists graph for which the smallest possible separation exists. So quantum chromatic number is 3, chromatic number is 4. But moreover, there exists a family of graph for which the separation is exponential. So these two parameters behave really differently. There are also known some bounds. This is at the best known bounds. So the chromatic number is always an upper bound because entanglement only helps. Like even if you have entanglement, you can always play classically. You can just disregard that you have this extra resource. So chromatic number is always an upper bound. And as lower bound, we have a version of the theta number. So the theta number was, a couple of people talked about it, was introduced by Lovash, is a semi-definite program. And there are a couple of different variations in the literature. And the one we're interested in is Szegedi theta plus number, which is thus just the theta number, but we add Szegedi adds some extra linear constraint. So this is still a SDP. And these are the best known bounds, and we actually gonna see one way we can prove these bounds. So what's the question? So this is everything, all this was in, unless these bounds, but this is part of the literature. So what we would like to do is, can we say something about the computational complexity about this quantum parameter? Can we find better bounds? Okay, so now let's go to a formal definition of the quantum chromatic number. I tell you only the story behind it, but there is a formal mathematical definition. So we saw that the chromatic number can be defined in such a 0-1 linear program. And now if the variables x, u, I are not assuming 0-1 values, but we now take positive semi-definite matrices, and we replace the constraint in the most natural way, this is exactly the quantum chromatic number. So now instead of scalar multiplication, we ask trace in a product, and now instead of summing up to 1, we ask the variable to sum up to a matrix row such that the trace of row is 1. So this is one equivalent definition of the quantum chromatic number, and the idea is the following. So this program is a minimization problem which asks the existence of some positive semi-definite matrices with some linear constraint. And the idea is to transform this problem in a conic optimization problem. Sure. So there is no size bounded, it must be finite. That's the only thing.
How many quantum states, how many quantum bits do they share everything?
So it's a similar question in the sense that there is no bound on how many quantum states they share.
Sort of, but fixed. I mean, it's fixed.
No, it's not fixed. So the idea is that you allow them to have as many entanglements as you want. So in some extent, as many quantum bits as you want. But it must be finite. But you don't have bounds. Having bounds on a finite dimension, this is another problem, and it's really hard. So okay. So the idea is to transform this in a conic program. And the cone we're looking is the following. So given a symmetric matrix M, we say that it has a PSD factorization if there exists a set of positive semi-definite matrices AIs such that the ij entries of M is equal to the inner product between AI and AJ for every ij. And the cone we're looking at is the cone of symmetric matrices such that as M as a PSD factorization. Okay, so we ask for the existence of positive semi-definite matrices such that their inner product gives the entries of the matrix. And we call this cone completely positive semi-definite cone. This is a cone, so that's easy to prove, but we cannot even prove that it's closed, or we don't know if it's closed or not. So that's an interesting open question. A couple of kind of easy observation you can say about this cone is that the completely positive cone that we heard of yesterday is contained in the completely positive semi-definite one. Why? It's one definition of completely positive you can think as the existence is a matrix for which there exist non-negative vector such that the ij entries of M is the inner product between these non-negative vectors. And now, if this vector, you just put them in a diagonal, you put them in a diagonal of a matrix, you obtain positive semi-definite matrices, and the entries, the inner product is going to be the same. So every matrix which lies here lies also in this other cone. We also have that a matrix which is completely positive semi-definite is double non-negative. So is a positive semi-definite matrix with no negative entries. And also the reasoning why this is so is really easy. So if we have exist positive semi-definite matrices with this property, so we can just vectorize the matrices. And so we have that a matrix here is positive semi-definite because it has a gram representation. And now inner product of positive semi-definite matrices is non-negative. So we know also that the matrix is entry-wise non-negative, so is double non-negative. So a classical result in the literature is that completely positive and double non-negative collapse for n is smaller or equal to 4. So this cone lies is exactly equal to the double negative cone or the completely positive. It's also known that for n bigger or equal to 5, a separation exists, and a separation exists also between these three cones.
So it is close to those values of n also.
Sorry?
For n at most 4, it's close to this cone.
Yeah.
What about n equals 5? Is it closed for n equals 5?
We don't know.
I think that the closure is known. I think there's a reference to this, but we could talk afterwards.
Okay, I would love to hear.
Yeah.
Okay, so I will say 2 words about what happens for the case of n is equal to 5. So this is an example of a matrix which is double non-negative but not completely positive. And a little lemma we can prove is that a matrix n by n which has support the n cycle, and a matrix that support the n cycle you can think as a matrix which the only non-zero entries are the diagonal one and the first off diagonal one. So a matrix of such a form. So this is a matrix which has support the 5 cycle. For such a matrix, we can prove that X is completely positive semi-definite if and only if is completely positive. So now this matrix has support 5 cycle is not completely positive. So we get it directly that it's not completely positive semi-definite. So we have one direction of the separation. The other one was found by Fuzzy and Parillo. They found a matrix which is completely positive semi-definite but not completely positive. And in particular, this implies that the Horn matrix, which we saw yesterday, is not in the dual of the cone. So let's look at what's the dual. So the dual of completely positive is the copositive cone, and it's the symmetric matrices such that the polynomial that you can write as the sum of mij xi square xj square is non-negative for any vector x in R. So the dual of the cone we are looking at, it asks symmetric matrices for which the sum of mij xi square xj square is trace non-negative for every symmetric matrices of dimension d for any d finite. So this is the dual. Now, this Parillo hierarchy for the completely positive cone. So we call Pmx the polynomial, which is written as the sum of mij xi square xj square, where we look at a commutative variable, and the R level of the hierarchy asks whatever is the matrices for which Pmx multiplied by the sum of xi square, everything to the power R is a sum of square. And this hierarchy, it's a hierarchy. It is contained in completely positive, and it also converges. So it's a natural way to build a non-commutative version of this hierarchy. So now we look at the polynomial Pmx, which is the same form, but we are looking at non-commutative variables. And now the R level of the hierarchy asks for symmetry matrices M, such that the polynomial Pmx is in the tracial quadratic model of the ball, which is exactly the non-commutative version of this requirement here. So what can we say? So in the non-commutative hierarchy, it's always so for every level R, the KR and non-commutative is contained in the KR. And equality holds only if and only if R is equal to 0. It is a hierarchy, and it is always contained in the completely positive semi-definite dual. The problem is that we don't know whether the hierarchy converges. And Klepp and Schögenhofer proved that somehow this is related to Conners embedding conjecture, which is a really deep conjecture in operator algebra. So we are looking in a special case, but in more generality, this problem it's equivalent to Conners embedding conjecture. Okay.
Would this not imply closeness then of the original semi-definite?
If you have convergence.
If you have convergence, then it would imply that the cone is closed, right?
Yeah.
Because it's the intersection of closed sets, the dual cones of these.
Yeah.
Or are these non-commutative not closed?
No.
The hierarchy cones.
No, these are closed.
These are closed.
Yeah.
So closed convex cones. The dual cone is closed convex intersection.
Yeah. But I think asking whether this hierarchy converges is probably a much harder question than asking closure. So
Conceptual, that's what I said.
yeah, yeah. So I'm trying to focus more on closure right now, but maybe he has a reason.
But you're not intersecting, right? You're getting them bigger.
No, the dual on the dual side. This is the dual cone.
It would no, but these are getting bigger, right? So
Right. So the dual side, the dual cones of these are closed convex cones, and they shrink.
But you want convergence of this, not in the dual.
No, what I was saying is, if this converges, if the answer is yes, the other answer would also be yes.
But to the dual, to the double dual of it, so the close, it would tend towards the closure of it.
Right.
Let me ask an easier question. Do we know that this cone or its closure is not semi-algebraic?
We don't. No, we don't.
Thank you. Okay, so let's now. So these are more open questions and things we're trying to work on. Let's say some result that we can have. Some more positive side of the story. So we saw that we defined the quantum chromatic number as existence of positive semi-definite matrices with some constraint. Now we introduce this cone because we want this to write this program as a conic optimization program. So that's what we're going to do, and the cone we're going to write this optimization program is exactly the completely positive semi-definite cone. So this is an equivalent formulation of an equivalent definition of quantum chromatic number. Now we have seen this relationship between cone. So kind of a natural question is say, okay, now we have this program, we are optimizing over this cone. What happens is, for example, we substitute this optimization program over the completely positive semi-definite to the completely positive, and we kind of get a nice result because when we do that, we get exactly back the classical chromatic number. So it was known that the chromatic number can be written as a copositive programming, but this is another reformulation. So let's do the same if we optimize over double non-negative, and we get exactly the theta plus formulation of Szegedi. So just because of the enclosure of the cones, we get directly these bounds, which are the best known bounds on this parameter. So let's get to the conclusions. One thing I want to stress is, for the purpose of this talk, I talked only about this quantum chromatic number, but this is not the only parameter that we can reformulate in this cone. And so this parameter they appear in the case of non-local games, but also in zero-error entangled-assisted quantum information theory. So there are a kind of a series of parameters we are looking at. There are 4 different parameters. So if you see a Q, it's because we're looking at non-local games. If you see a star, we are talking about zero-error information theory. And just because of the relationship between the cones and playing with the optimization programs, we get these bounds between the parameters. And these are the best known bounds. So the aim is maybe the initial question about this parameter is really, what can we say about computational complexity? What can we say about better bounds? Because we saw like the difference between quantum chromatic number and chromatic number can be exponentially bigger, and it's also actually not known whether any of these inequalities is strict. So that would be an interesting question. So the aim is to look at this conic approach to build converging hierarchies, and hopefully even computable. But this cone, probably few of you in the audience are familiar. That also appears in the context of PSD lift, so extended formulation. So it's a natural cone to look at. And there are many open questions in the field. Thank you.
Questions, please.
I mean, there is this famous PRE paradox in the quantum theory. Like, can you give? I mean, I don't know whether you know the paradox. So Alice and Bob flip a coin.
Yeah.
If the answer is, if the result is different, then they win. If the result is the same, then they lose. And if you don't have quantum information which is shared by them, then the probability to win is 3/4, of course, and you cannot do better, no matter what the strategy is. And if they share quantum bit, the probability can be higher.
Yeah, so cosine or, yeah.
Okay, so can this be explained in terms of the chromatic number of the quantum chromatic number of some graph?
Okay, so now the reason why somehow the formulation of this parameter is quite clean, and we can do this conic approach, is that we disregard the probability of the games. So what I want is, in the local games, I just care that the players always win. I don't really look at which probability they win. So probability of winning is equal to 1. Now, in the type of games you have in mind, what you want is you have the value of the game is given by the probability of winning, and then you look at the probability of winning when you have a classical strategy versus with a quantum strategy. But here, the probability, I want the probability of winning to be equal to 1, and now I'm looking to another type of value of the game.
Quantum theory is sort of in part probabilistic in nature. I mean, what does it mean to have probability?
No, but so because what we are optimizing, like what the value we require is the amount of answers they can give. So in the chromatic number case, we look how many possible outputs they can give. So it's another way of looking at the problem. Somehow this theoretical framework is a bit easier. So.
And I have another question.
I wanted to ask, so can you squeeze in the fractional chromatic number in this frame, or is your Q chromatic number no relation to the fractional chromatic number?
There is no relationship with the fractional chromatic number. What is not known is wherever there is any relationship with the minimal dimension of orthogonal representation. So this psi introduced by laws. But the fractional chromatic number is you have graph which is lower and you have graph which is higher.
So the hierarchy for the dual code, is it the spectrahedral hierarchy? So all these KRs are spectrahedral code? Did you try to compute them or, plot them or something like that?
No, no.
Okay, did you try to also find, because we have examples in the completely positive side, we have, so it's the double non-negative cone is different than this cone different than the completely positive. But in the dual side, there's one inclusion that we don't know if it's strict or not, like the p plus n and this cone, the dual of this cone. Did you try to check using this hierarchy if it's to find a counterexample or something?
No, we haven't looked really much at the dual yet.
Okay.
So.
Last quick question.
Okay, and the question is, can one characterize the quantum chromatic number in some intrinsic graph theoretic terms, like in terms of minors or whatever?
Oh, that would be, if you could do that, that would be really interesting. But the thing is, it's really hard to understand how can you compute this parameter and how you actually. I don't really believe it's going to be a classical characterization of this parameter.
Okay, because it's so weird, right?
It is really weird.
Okay.
With more questions, please, directly to the speaker after. Thank you again.